Okay, welcome to the notes on 9.2 and 9.3. We're going to go through 9.2, which is solving quadratics by graphing, and then 9.3 is transforming quadratic equations. So let's take a look. We've solved by factoring before, and we've solved by taking the square root of both sides. And so this is just another method of solving. A quadratic equation can be written in the form ax squared plus bx plus c. We know that when a is not equal to 0, because that's the form we use when we put it in our graphing calculator. And we've talked about this a little bit in class, that the solutions to this graph are the roots, or the x-intercepts, or the zeros. Remember, we had all those different names. So if we graph a quadratic and it has two unique real solutions, that's when it intercepts the x-axis. Sometimes it'll just touch the x-axis at one spot, and then sometimes it doesn't touch it at all, so it has no real solution. So those are our three options. We've talked about that before in class. So really all you have to do, and you can graph these by hand or on your graphing calculator, you make sure it's set equal to 0. You graph it either using a table of values. You can graph it using what we've already done with the axis of symmetry and finding the vertex. You can do all sorts of stuff. You pick how you want to graph it, but once you graph it, you graph, and we get an answer. So let's take a look at 1a. If we were to graph that, what that would look like. So let's go ahead and, well, I'll just do a table of values. We have x and y, and you'll notice up here on the example, you can check your answers simply by putting in the solution. So we'll do that at the end also. Okay. So let's just graph it. Let's pick some numbers. So -2, -1, 0, 1, and 2 are really common choices. So when we put -2 in for x squared, we get 4 when we square it. So that's -4. We get minus -6. That's plus 6, and then plus 18. So the reason I did that up here is so that we can see when we put -2 in, we're going to get positive 20. That's going to go off my graph, okay? So I want to kind of adjust my numbers. I want some smaller numbers. I mean, -220, that's like way up here. Okay, so let's try and pick, if you pick 0, I mean, it's easy to start sometimes just by picking 0. Sometimes picking points is the hardest part. 0 is going to give us the y-intercept. If we put 0 in for each of these, that's going to give us 18. That's way up here also. So what if we pick like 5? Let's pick 5 and see what we get. Okay, so that's 25. So that's -25 minus 15. So that's -40 plus 18. So that's 22. So that's too big also. Okay, let's try 4. Let's pick 4 and see what we get. So that's -16. And some of this is just the guessing that we have to do to get what we're looking for. So 4 gave us 10, so that's 10, so that's better. Still no room for that on this graph. Let's go 3. What if I do 3? So let's see. 3 would give me -9 minus 9 plus 18. So 3 actually gives me 0. So I would have, that's one of my answers now, I know that. Let's try 2 and see what 2 gives us. So that's -4 minus 6 plus 18. So 2 gives me 8. So 2 and 8. Okay. Let's see here. And 4 gave me 10. From looking at the numbers, one thing I'm able to tell about this graph is because this is negative, I know it's opening down. So I'm guessing the graph is going to go something like this and then down. I don't know where it's going to end up down over there, but just based on the shape of parabolas. So we know 0 is way up there, so I'm going to guess something like way negative, just so we can see if we can get more of this graph. So I'm going to go like -4. Okay, negative 4 gives me negative 16 plus 12 plus 18. So negative 4 is going to give me, you guessed it, 14. So negative 4 gives me 14. That's still way up here. It's on its way down. Let's try negative 5. So we have negative 5, so that gives us negative 25. And then that's plus 15 plus 18. So negative 5 gives me 8. So I'm here at negative 5, 3, 4, 5, so right here. So I can see it's starting to come back down. Let's see what negative 6 gives us. And you know, if you want, there's all sorts of other stuff you can do. You want to find the line of symmetry and make it easier for yourself, you can do that. Sometimes, you know, it just depends on the problem. You're going to have to try different stuff. When we do negative 6, we're going to get negative 36 plus 18 plus 18, which equals 0. So the parabola on this one is this shape here. It's way up. Remember, we calculated it's way up there. That's really curvy and not great. Sorry about that. But that's what it looks like. You know, sometimes the axis of symmetry will help you. If we found that, that would be 3 over 2 times a. So that's a is negative 1, so it's negative 1, right? So we know that, I'm sorry, negative 2. So we know that 1.5 is the line of symmetry. So what we can do at that point is we could draw that in. Let's do this. Let's just draw it right here. Negative 1.5 is here. Okay, so we could draw that in and then use the other points to find the other, you know, based on symmetry, and find the other points that way. So there's all sorts of different ways we can graph it. The answers here on this one we found, though, were 3 and negative 6. Okay, those are the solutions on that one. Let's take a look at this one. The numbers are smaller here. On 1B, it'll be a little bit easier for us. Okay. So let's see, we know 3 is the y-intercept. Let's do this differently. We know 3 is the y-intercept. X equals the opposite of b over 2a. So the opposite of b is 4, and 2 times 1 is 2. So the axis of symmetry is positive 2. So let's go ahead and change that. Positive 2 is the axis of symmetry, so it's right there. I know that it opens up, so I know there's another point here. I know the vertex is somewhere on there, okay? If I want to find it, the vertex specifically, I just put this 2 back in for x, and I get 4 minus 8 plus 3, which becomes negative 1. So the axis of symmetry is here. And then I'm pretty sure I've got, I can actually draw myself a parabola here. Let's see how well this goes. We want it facing up. So my parabola is something like this. Okay. And so I get answers that, you know, and again, that's a sketch. It looks like the answers are close to 1 and 3, and sure enough, if I put 1 in and 3 in, then they're both going to work if I plug them back into the equation. So on this one, we'd have x equals 1 and 3, that those would be the solutions. Okay? Let's take a look at another one. Sometimes we have what's called a double root. Okay, and we talked about this earlier. This is when we have a perfect square trinomial, and so there's only one number. Remember, when we solved these by factoring, a problem like x squared minus 6x equals negative 9, we got it equal to 0, and then we factored that, and we ended up with x minus 3 squared. Well, that meant that x equals 3 and x equals 3, so they're both at the same spot. So there's only one answer. There's one solution to these problems. Okay, let's add. Let's throw throw our graph back on just so we can make sure we see these. So here we have x squared plus 25 equals 10x. We subtract 10x from both sides. X squared minus 10x plus 25 equals 0. You choose whatever method you want to graph that, okay? And for whatever method, find the 25 is the y-intercept, so the graph isn't big enough for me to do that. If you want to find the vertex or the axis of symmetry or those kind of things, you do that. The opposite of b over 2a is going to be 5. If we factor this equation, I know I'm going to get x minus 5 times x minus 5. And so I'll go over here to 5, and I know that the parabola is there, something like that. I know it's opening up, so it looks something like this. Exactly what it looks like doesn't matter because we're looking for where does it intercept the x-axis, and it's right there on the 5. So x equals 5. Okay. Same thing for this second one. Hold on. For this second one, we're going to add 8x and add 16 to both sides, so x squared plus 8x plus 16 equals 0. I know that that's x plus 4 squared equals 0. You choose whatever method you want to graph that. The opposite of b over 2a is the line of symmetry. So again, we'd have negative 4 now. And because it's a perfect square, I know that my parabola looks something like this, but that the answer is negative 4. The solution, the x-intercept, the root, the 0 of the function. Okay. Sometimes we get numbers that aren't there at all. There is no x-intercept, for example, in this solution. So if there's no x-intercept, x-intercept, root, solution, 0, all the same thing. So if it's not there, then we have no answer. And when it's like any other problem we've done this year. If it's no solution, then that's what you write. You write no solution. So if we were doing this problem, we have negative x squared minus 3x minus 5 equals 0. Let's find the axis of symmetry. That's the opposite of b over 2a. So it's negative 1/2. So we have a line at negative 1.5. Okay, something like that. Let's plug negative 1.5 back into the original equation. So we have negative 1.5 squared minus 3 times negative 1.5 minus 5 equals 0. This becomes 2.25, so negative 2.25 plus 4.5 minus 5. Okay. Let's go into our calculator real quick, make sure we get all of our numbers correct. So that's negative 2.25 plus 4.5 minus 5, and that's 1.75. Oh, I forgot the negative there at the beginning. Sorry about that. 2.25. I knew that was wrong. 2.25 plus 4.5 minus 5. So I have negative 2.75. Okay. So that's negative 2.75 is somewhere there. Now, because this leading coefficient is negative, I know that this picture is going down. What exactly it looks like, it's not really my concern because I'm just looking for the solution. So there is no solution. Okay. If you want to try another one, go ahead and try 3b, but you'll get a similar scenario where you have a graph that's opening down and it's below the x-axis to start, so there's no solution. Some people might be wondering, well, what if I added x squared to that side and added 3x to that side? Then you'd get a similar function. It would be up here and it would be opening upward. So it doesn't really matter if it's a negative x squared or positive x squared, as long as you follow the algebraic steps correctly. So estimating a solution, sometimes the graph, it doesn't have integral roots. The roots aren't integers. So we'll estimate the solution and say it's about this or about that. We're really just looking for a ballpark there. Let's go ahead and take a look at our graphing calculator and get some practice with that. So if we wanted to put that in, we have 2x squared plus 6x minus 3. So I put that into my graphing calculator, I hit draw, and I get this. And then the directions say to the nearest tenth, so I can just hit G solver and roots, and it's negative 3.4 to the nearest tenth, and then I'm going to hit over once, and 0.4, so negative 3.4 and 0.4. Really easy when you know how to use your calculator. Okay, let's do a real world one. Okay, with the problem that we're given here, and I'll do this one in the TI. Okay, so this is about a goalie kicks a soccer ball with an upward velocity of 65 feet per second, and then they give us the equation, and we're saying that the ball was 1 foot off the ground when we started, and then how long was it in the air? Okay, so you have to find the roots using a graphing calculator, and the x-intercept of the graph is approximately 4, therefore the ball is in the air for approximately 4 seconds. So now we're saying, what if the initial velocity is 55 feet per second? Okay, 55 feet per second. So we're going to replace the 65 with a 55. Okay, so let's put that in the TI. So let's go, nope, that's my Casio. Let's go to the TI, and I'll go to y equals, and we'll say negative, and then 16 x squared plus 55, that's where we're changing the equation, 55x plus 1. Oh, no, sorry, they said in the question that 2 feet off the ground. His foot meets the ball 2 feet off the ground. Okay, let's hit enter, and let's graph that. Now, you'll notice that depending on what your graph looks like, and I'll change mine here to zoom standard, so that's zoom 6. So now, I can't see the whole graph, but I don't need the whole graph. The part that I need is this part here where it crosses the x-axis. Okay, that's the part we need. Alright, so let's go to second, calculate, and we're looking for the 0, so that's 2. And then we have to do this left boundary, right boundary stuff. So I don't want this 0. I want this one. I want to know how long was the ball in the air. So if you think about the soccer ball, it's getting kicked up and then back down. So when it says left boundary, it wants to know, are you on the left of the intercept you're looking for? Now I'm going to move this. I'm hitting the directional pad to the right just so I can move over to where I want. So there, now I see it again. I'm on the left of the 0 that I'm talking about, so I hit enter. And then I go down here, and now I'm on the right of the 0 that I want. So I hit enter, and then it says, do you want me to guess? It doesn't say, do you want me to guess? It says, guess appears on the screen. I hit enter, and it tells me that the 0 is 3.47, so I'm going to put about 3.5 seconds. Okay? A little more complicated in the TI, but you feel better about yourself because you have a TI, and people think nice things about you. That's it for graphing, solving by graphing. It's really quite simple, to be honest. Sometimes it's easier in calculator, sometimes it's probably easier to do by hand. It depends on how complicated the equation is to start. Now we're going to look at transforming quadratic functions. So we'll see what that means. A transformation is oftentimes thought of in geometry, but it exists graphically also. A transformation changes the position or size of a figure. One transformation, which is called a translation, moves a figure up, down, left, or right. When a constant c is added or subtracted from the parent function, the graph of the resulting function is the graph of the parent function after it's been translated. Okay, so real quick, sort of to understand this, if we take the parent function of all parabolas, which is this right here, okay, and I shouldn't have done that in red because the other one's red. So it's this right here. So that's the parent function. Okay, that's y equals x squared. If we say y equals x squared plus something, then it's going to take that graph and translate it and become this one. If we say y equals x squared minus something, then it's going to take that graph and it's going to translate it down here. Okay, so it's shifting it up or down. So for example, describe how the graph of each function is related to the graph of f of x equals x squared. So h of x in this case equals x squared plus 3. If you were to describe that, since the value is 3, the graph is translated up 3 units. That's all you have to do. The graph here, because it's minus 4, has been translated down 4 units. So if you look at these, you just need to determine, is this going to translate it up or down, and by how much or how many? So when we look at 1a, this is a translation down, because that's negative, and it's down 7. And that's all you have to do. Okay? If you look at this one, this is x squared plus 5. We can change places there. So this is up 5. If we look at this, and this is where we have to understand, x minus 5 plus x squared is the same thing as x squared minus 5. So this is down 5. And then if we have x squared plus 1, this is up 1. I didn't like that font. So there's some new font. So down 7, up 5. Down 5, and up 1. All right. Another kind of dilation, or another type of transformation is called a dilation. A dilation makes the graph narrower than the parent graph or wider than the parent graph. Okay, we have dilation when we have the original x squared is multiplied by something. So this is when x squared has a leading coefficient. If the x squared, if the a in front of the x squared, if it's greater than 1, okay, if the absolute value of it is greater than 1, then we stretch it vertically, or you can think of it as getting skinnier. If the absolute value of a is less than 1, then it's compressed vertically, or you could think of it as getting fatter. All right, so let's take a look at an example here. So we have x squared is the original, that's the blue one, and if we put a 1/2 in front of it, we would say that it's being compressed vertically, okay? That it's compressed vertically. That's what's happening, okay? So it's almost like compressed means like being squished. And so this green function now, it's compressing it vertically. It's pushing it down. Here, if we have 3x squared plus 2, that's two things are happening to it, right? It's getting stretched vertically, and it's been translated up. So it's up and stretched vertically, right? So let's look at this one. 2a, that's going to be stretched vertically, okay? That's stretched vertically. Because the coefficient is greater than 1, all right? If we look at 2b, in 2b, this is going to be stretched vertically because that's greater than 1, but it's also going to be shifted down 2, okay? Down 2 and stretched vertically, so it's both. Okay. And then if we look at the last one, this is going to be up 2, and then it's going to be compressed vertically. Compressed vertically. Don't worry, you'll see the words, they'll appear. Compressed vertically. See, and you were worried. Alright. A reflection, it flips a figure across the line. It's a mirror image. So if we take x squared and we just make the coefficient negative, then it flips it. Okay, that's what happens here. When the x is multiplied by -1, okay, x squared, or the variable x, is multiplied by -1, it's reflected across the y-axis. All right. So if we look at this one, describe how the graph of g of x equals -2x squared minus 3 is related to the parent function. So that's a few things happening, okay? It says there's 3 separate transformations. We know that because we have a negative, we have a coefficient, and we have a number afterwards. So what we have is the negative sign causes a reflection. So that's 1. So we have a negative sign, so that's a reflection. Then we have a dilation and a translation down. Okay, so it's reflected across the x-axis, compressed, and translated down. All 3 of those things. Sorry, one thing back real quick. I want to make sure we understand this. That if the negative is outside, it's a reflection across the x-axis. If the negative is inside, it's a reflection off the y. And the reason I bring that up is because if you look at the first example, the negative is inside. Okay, so this graph right here is going to be reflected across the y-axis. Okay, that's one thing. It's going to be stretched 2, right? Stretched 2. And then it's also going to be, because of this 9, it's going to be translated down 9. Okay? If we take a look at, that says Q, not 9. There we go. If we take a look at the second one, here the negative sign is on the outside, so this is going to be reflected across the y. Okay, again, a reflection. It's going to be shifted up 3, and it's going to be compressed because that coefficient is less than 1. Okay? And again, the nice part about all these is you can put them right in your calculator and check these answers. Okay? You can use what you know about the characteristics of graphs of quadratic equations to match an equation with a graph. So this is just, can you figure out which of these is this graph? Okay, that's really all it is. If you're ever not sure, you can always plug stuff in. Yeah, you'll notice that the graph, this is the example, and it says you'll notice that the graph opens downward. Since it opens downward, there are ones that we can eliminate. It opens down, so we know it's not that or that. Okay, so we can eliminate A and D. The parabola is translated up 5 units. Well, this would be down 5 units, so we can eliminate that. So we know our answer is C. Okay, pretty simple, just by using what we know to figure it out. So let's take a look at number 4. This has been shifted up 1. Let's start there. So this has been shifted up 2. That can't be it. This has been shifted up 1. That one's up 2, so that can't be it. Here we have a negative exponent, so we know it's opening down, so it's not F. So really simply, the answer is H. Okay. That's it for this. There's a lot here that you can do in your calculator. This would be good for us to get good at using our calculators. Here are the check your understanding problems that you're going to want to work on from each section. So there's 1 through 9 and 1 through 7. Feel free to pause the video on those. Give those a try. And when you get to class, we'll work from the hard problems backwards. All right. See you guys next time.